Hello, my name's John Ludlam, and I'd like to give our talk today titled The Final Pieces of the OCaml Documentation Puzzle. This talk is about Odoc, a tool for generating documentation from OCaml source code, for which I am the current overall maintainer. In particular, I'd like to discuss some of the innovations we've been working on over the past year or so to make Odoc 2.0 that we believe will make this the best tool for documenting your OCaml projects. Let's start by stating some principles of good documentation. Documentation should be correct. I hope this is a pretty uncontroversial statement. It's worth saying though, as the currently released version of Odoc produces documentation that is, in a few cases, incorrect or suffers from broken links. Secondly, it should be useful. By this I mean it's got to show you what you want or need to know in an obvious way. I'd also like to state clearly how the generated documentation will be consumed. As with most other code documentation tools, we will focus first on generating static HTML. As we'll see later, we can then adapt this for other output formats, such as LaTeX or man pages. Finally, we'll be using module signatures as the basis for generating our documentation. So, why is this tricky? Why has it taken such a long time to get even where we are today? Well, signatures are indeed a great starting point. Modules, the building blocks of OCaml programs, and the signature is the surface that's exposed to other modules. Documenting the signatures by looking at the MLI files, or actually the CMTI files, therefore makes a great deal of sense. However, the actual text of the signature might not be terribly illuminating. Let's look at an example. This is taken from Jane Street's base library. It's a great signature for its intended purpose, constraining the content to be correct. The aim is extending the S-expression module, keeping it compatible with the original. It begins with this slightly convoluted construct, include module type of struct include sexp, to pull in the signature of that module, making sure that the signature is strengthened, such that the types we pull in are equal to the types in sexp. The extended functionality we want is then in a standard set of comparison functions, so we pull in the comparable.s signature, using the destructive type substitution t:=t, to make sure that the extra functions will be operating on the correct type. It's precisely what's needed and no more. So let's see what OCaml doc makes of it. So what can we see from this? The clickable links, sexp and comparable.s, that take us to the definitions are great. We certainly want to keep this sort of functionality. But not much else is great on this page here. It doesn't really pass our second principle. It's not very useful. I've no idea from this what types and values this module actually contains. We could really do with showing what the includes here end up including, the types, the functions and their associated docstrings. This is what we call expansions. Now it's not just includes that we're going to need to expand. The signatures of modules and module types are often described by referring to other module types, sometimes with additional type or module equalities or substitutions. Sometimes they're not, they're just signatures, in which case we don't need to do any extra expanding. We also need to do some similar expanding for classes and class types, though this is an area we're still working on, so I'm not going to go into any detail on this today. We've also got the option of what to do with the expansions. For includes, we put the expansions inline in the page. For modules and module types, for HTML, we generally will create a new page with their contents. Different output formats can decide on how to deal with them in different ways too, which we'll come back to later. We also need to consider how the expansions will affect the destinations of the various clickable links. The process of deciding this is called resolution, and is done for both links found in code, called paths or fragments, and those found in documentation comments, known as references. So, how are we going to calculate these expansions? The first and most obvious thing to do is see if we can just ask the compiler. Can we get away with just getting the compiler to do all the work, and then we just present it? Well, yes and no. We do indeed get the compiler to do a lot of work, and Odoc operates using the typed trees as input. That is, rather than reading the MLI files, it will read the CMTI files. This has the extremely useful property of ensuring that we're only ever dealing with correct input. However, the problem with these expansions is that what the compiler wants and what we need are not entirely aligned. The compiler only really cares about the resulting signature and not what went into making the signature, whereas we want to track the provenance of elements in the signature so we can show where they came from and link back to their definitions. What the compiler has calculated will have all the includes, the types and module substitutions, the type of expressions, simply replaced with their results. Additionally, all the comments are gone, so the actual documentation is missing, which is definitely a minus when it comes to producing the docs. So we need to write our own code to do these expansions. The currently released version of Odoc has a very clever but quite bespoke implementation of expansion and resolution. This was very good, but not perfect, and also quite hard to understand. This made it tricky to keep up with the compiler as it added new features, and there were some long-standing issues that were very hard to fix. Over the past year or so, we've implemented the new model to do the work of expansion and resolution, which is based on how the compiler itself works, whilst keeping better track of where signature elements come from. One of the most important implications of this approach is that Odoc ends up inheriting a two-pass approach corresponding to compile and link, which I will talk a little bit more about in a second. However, let's look first at the output of Odoc 1.5.1, the currently released version, and the current master branch of Odoc, working on our previous example. Now, I'm not using the real S-expression and comparable modules here, just some stubs to show how it works. You can see here that the includes have been expanded to show their contents. However, you can also see a number of problems here. Firstly, there's this odd lib__sexp.t. There are no source files containing double underscores. Secondly, I did actually write a doc string for the function ofString, which has disappeared. Thirdly, the destructive type substitution hasn't happened. The expansion of comparable.s still has a type t in it, and the function le below contains links to that type. If you click on them, it takes you to the line above instead of to the top definition. So this fails on principle 1, it's not correct. So let's now take a quick peek at the improvements we've made in master. This is the same as rendered by the current master of Odoc, more or less. This is just to point out that the issues in 1.5.1 have been fixed. In basing our implementation on how the compiler works, we need to process our inputs in much the same way as the compiler does, and we've named them similarly. We start by compiling the CMTA files into Odoc files. As for standard compilation, if your module depends upon any other, that module will have to have been compiled first to produce its Odoc file. Linking is then the next step. When we link, we resolve all of the references and doc comments, which could be to any module in this package or any dependencies. As such, linking requires all of the Odoc files for those to have been compiled too. Once the linking is finished, we have a self-contained OCaml file. We're then in a position to use this to generate any of the output formats. A single OCaml file will often result in multiple output files. Let's now talk about some of the challenges we've encountered along the way. Some of these are minor and some are pretty tricky. Let's go through them one by one. The long-term goal in OCaml is to do namespacing using the module system. We'll pack all the modules to do with a particular library into one top-level module and not have to expose the individual modules that make it up. Once we've got first-class support in the language, we won't have to worry about having canonical modules, but for now, Odoc has to help maintain the illusion that it's already there. This is how it works today with Dune. We write our modules, here, x and y, as we'd like them to appear within the library namespace. We can just refer between them just as x and y as usual, as long as we don't cause dependency loops. When we come to compile them though, Dune will tell the compiler to ignore their file names and that their names are actually lib__x and lib__y. Now this would break the intermodule paths like x.t. Dune will actually first generate a new file, lib.ml-gen, that contains aliases to the short names x and y, from the short names x and y to lib__x and lib__y. Now, even though this file refers to lib__x and y, it can be compiled before them with the help of the compiler flag noaliasdeps, because nothing in these files depend upon the contents of those modules. The generated file makes a note that to link it will require lib__x and y like normal, but obviously it can't record the hash that it would do normally. Then when we compile x and y, pretending that they are lib__x and lib__y, we instruct the compiler to open the module lib, which brings the short names into scope and allows the files to compile as if their names hadn't been mangled. When we then want to use this library, we refer to modules lib.x and lib.y and pretend that lib__x and lib__y don't exist. So how does Odoc deal with this? Well, because we work in the same way as the compiler, we deal with it in the same way that the compiler does. First, we compile the generated lib module. We make a note that the paths to lib__x and lib__y are forward paths. That is, we haven't yet compiled the Odoc files corresponding to these modules. And we write out lib.odoc. We then compile lib__x and y. When it looks at x.t in module y, because it's operating on the typed tree, it knows that the x is the x from lib.ml. So it looks up the module x there and notes that it's got a canonical tag in front of it, and records this in the path. Semantically, this means that references to that x should be referred to lib.x, and therefore the reference to x.t should go to lib.x.t. Now that Odoc has compiled the files, we get to the link phase. Since we're trying to pretend that anything with a double underscore doesn't exist, we don't link those files, so the only file we actually link in this example is lib. We look at the module aliases here and note that they are self-canonical, that is, the canonical path to the module is in fact this module. We therefore expand the aliases and splice in the signatures from lib__x and y. We then recursively link those expansions, and in this case we'll resolve the x.t path, looking up the canonical path so that the link will be to lib.x.t. We actually do check that the target exists to ensure that we have no broken paths. For any links that can't be resolved, we'll report this and just output text rather than a link. So this is a slightly more advanced namespacing example. The difference here is that we've handwritten our lib.ml file, and so the generated one is now lib__.ml. This is more expressive and allows for finer control over the top level module, but now you have to be much more careful that the canonical links are correct. As you can see, the canonical tags in the generated file are still pointing at lib, so they're pointing into the handwritten file. If you've chosen not to expose a module, or you've changed its name, the canonical path won't resolve correctly, and this can lead to unresolved paths. As I mentioned previously though, we do check everything and can report if this sort of thing is broken. We don't ordinarily expand module aliases unless they're canonical modules as in the previous slide. It's not necessary because the module aliases are real aliases and there's no need to simply duplicate the contents. Additionally, it does enormously help reduce the size of the docs we produce. The downside is that it complicates linking to definition points. In the example here, we need to ensure that the link for x.t points actually at y.t, while the text of the link remains at x.t. Now, this is another example of Odoc attempting to keep track of the provenance of items more carefully than the compiler. Here, we've got a module type sig that contains an opaque type t. Then a module type mod type that contains two modules, x and y, that both have signature sig. Lastly, we'll declare a module m that has signature mod type with an additional type equality x.t equals foo. Now when the compiler evaluates the signature of module m here, the definition of x within is simply replaced with a signature, and we lose the fact that it originally came from module type sig. Odoc tries to be more careful and instead will keep the sig on x and instead annotate it with the type equality t equals foo. Shadowed items came in OCaml 4.08 as a way to make overriding included modules simpler. Here, the issue is that we must be very careful in expanding the include so that we don't accidentally end up with duplicate module definitions. In this example, foo contains a module bar, which you can see because we're explicitly referring to it below. We're including foo, then overriding bar, extending it with a new value, baz. If we didn't remove the module bar from the include of foo, then we'd end up with two bar modules. Now, as I mentioned earlier, the links taking us to the definition points of items were really good. In fact, much better is for a link to a module or a module type to take us to the contents of the module. However, to do this we need to check that the module is not opaque, as then it won't have any expansion, and therefore trying to link to the contents would result in a broken link. I've not yet talked much about references, which are links to items found in documentation comments. Obviously the compiler simply ignores these entirely, so the resolution of these is entirely up to Odoc. These are mostly more expressive than links found in code, which can only refer to types, modules, module types, classes, and class types. References can refer to many more objects, such as constructors, values, or record fields, and they can also project elements out of module types. You can't refer to elements in a functor application, though this would be simple to add now. To be as general as possible, references are not resolved until link time, and thus we can refer to any element defined in the whole package or dependent packages. Now we're getting a little bit more off the beaten track. I'm not going to go into any detail on dependently typed modules. Suffice to say that we have to be even more careful when functor results depend upon the module types in their arguments. Please ask me afterwards if you're interested. Now, there are some other interesting features, but now I'm going to move on to how we've added a document intermediate representation to allow us to simply generate different format outputs, such as LaTeX and man pages. Once we've finally done all the resolving and expanding, compiling and linking, the output from the model layer is effectively a syntax tree that fundamentally has the same shape as the typed tree from the original CMTI file. You have to know quite precisely how OCaml works in order to traverse it effectively. To simplify backend logic and to reduce code duplication, we first transform this syntax tree into a document-oriented intermediate representation. This is designed such that backends can traverse it simply and concentrate on generating the appropriate output for the backend type. Naturally, different output formats have different capabilities. HTML can split things into small pages with links between them, whereas printed LaTeX-based documents should not be treated in the same way. This intermediate format therefore has to be rich enough to support a variety of output formats, whilst being agnostic about the actual language being rendered. To add a new backend then is simply a question of providing a function to walk this tree and render the appropriate output given a provided formatter. Traditional document representations, such as Pandoc's internal data types, usually have a split between block items, such as paragraphs, lists, headings, and so on, and inline elements representing styling like bold or links to straightforward links or straightforward text. Code is naturally more hierarchical than this, so we have more of a tree structure, but broadly we have the same sort of split. We have items, which are the equivalent to blocks and contain headings, documentation blocks, as well as declarations such as modules, types, and values. We also represent includes at this level to enable the HTML renderer to interactively allow them to be opened or closed. The declarations are then constructed from annotated code, which represents code with additional metadata associated with it. This additional metadata may be a documentation block, an alternative representation. For example, modules might have a short and long expansion, the short being an abbreviated sig.end, or possibly a path to a module type, and the long being the full expansion including all of the declarations, again a list of items. Here we can see an example of this in action in an excerpt from the alcotest package. The HTML renderer inlines the short expansion and renders the long expansion as a subpage, whereas the man page renderer might put the puts the long expansion in line, as you can see here. I'd like to talk a bit now about our future plans for Odoc. It's an exciting time as with these recent improvements we're now in an excellent position to make some really interesting advances. The first thing we've got planned is moving the rendering of the standard library documentation for the OCaml manual to Odoc and slowly deprecating OCaml doc. It's likely this will follow a similar path to CAML p4, moving it out of the main OCaml repository to be maintained separately. I'd be very interested to hear from anyone for whom this will present any challenges. We're eager to work with people to find solutions, so please get in touch. We'd like to add search to Odoc soon. This will likely depend upon handling implementation as well as interface files in order that we can rank the results according to the amount of usage. We'd like to revamp docs.ocaml.org as a central repository of docs for all versions of packages. This is an interesting challenge, not least because the contents of a package is dependent not just upon its own version, but quite possibly on the versions of the packages it depends upon. Then, how we integrate with the rest of the OCaml documentation ecosystem, for example MDX, is also something we'd like to address. For example, we're currently looking at mapping between Odoc syntax and MDX. Perhaps also you can even use Merlin for looking up docstrings. If you're interested, please do come and talk to us. So thanks here to everyone who's contributed to this work, the new model, myself, Leo and Jules, the new document layer and man page and HTML renderers by Gabriel, and the LaTeX renderer by Florian. Also, to everyone who's contributed to Odoc in the past, particularly Anton Bachin, from whom I've only recently taken over as overall maintainer, who did a fantastic job over the past few years. Thanks very much for your attention.